Ladies and gentlemen, welcome to this lecture about the input signal selection for nonlinear time history analysis. So today we will see a number of prescriptions for generally European standard codes according to the Eurocode 8, which is actually the standard code related to the seismic assessment of structural systems. And then we will see the differences actually between the Eurocode 8, so the European standard, and the Italian building code. Generally, the Italian building code is has been derived from the Eurocode 8 standards, but actually there is a lot of new prescriptions since the Italian building code has just been revised in 2018. Whereas concerning Eurocode 8, it is actually under review by special committees, which actually contains special experts worldwide in generally seismic assessment of buildings and bridges. So we are expecting some modifications in the code in the near future for Eurocode 8, and we can see some of them maybe also in the Italian building code where the review has been already done. And I will provide you some useful tools to actually provide a suite of natural seismic events for our assessment for nonlinear time history analysis. And I will show also how to try to control the main rules behind the spectrum compatibility of the selected events. So we will try to use the database of all the seismic events which are actually considered within a software, and I will show the software also. But one of the most interesting aspects of this software is not only that it is actually modeled within the MATLAB environment, but it is actually an executable file which is separated with respect to the MATLAB environment, but actually it is developed within MATLAB, because within MATLAB we can also develop some not only scripts but also a graphical interface softwares, so that it is possible also not only to write scripts but also to see what we are actually setting in our programs. And the best thing is that this software actually provides in the installation folder the whole data set in terms of workspaces of MATLAB environment. So you are able both to load all the events, not only the time series of ground motion along all the directions X, Y, and Z, so the three-dimensional event. Not only that, but there are also already computed response spectra for all of them. So you will see we can just consider the already computed spectra in order to do an initial selection, and then we can modify directly the records in order to come up with the final suite of earthquakes that we have to apply to our buildings. And tomorrow we will actually do some assessments through the commercial software SAP 2000, and the main goal will be actually to be able to perform nonlinear time history analysis. We will check how long it takes to perform all the computations, and we will try actually to get exactly the same results within the shortest time possible, by changing some assumptions and some modeling issues within the model. Obviously, we have to check, depending on the the size of the final of the final model. We will check how long it takes actually to perform all the computations. We know that generally nonlinear time history analysis are quite long analysis to be run, and depending on the the high nonlinearity that we model within the structural system, we can also have some problems in convergence. So I will give you also some issues some suggestions to solve some issues about convergence, and it is actually what I found during my activities, and they are just related to some values that are generally applied as maybe very large values for stiffnesses, for instance, in the vertical direction. So as soon as we apply very large numbers, maybe there would be some numerical inconsistency, and so we are not able to achieve actually convergence. So before starting again, do you have any question about what we are seeing yesterday, and generally some doubts about what we have discussed up to now? Okay, so if it is not the case, let's start. I share my screen. Okay, so let's start by seeing some aspects about the selection of the seismic input for nonlinear time history analysis. So I will go very briefly into details, just because I surely know that you are already familiar with all of this stuff. But then we will try to directly do something practical, so we will be able to use a software and then to analyze one by one all the events. So we know that if we have a highly nonlinear system, we do need to perform nonlinear time history analysis, which is the time responses according to the time history of ground motion. And this is actually the case for isolation systems, because generally we have, at least we have rubber bearings, which can be modeled through a linear spring. You have seen last week what I mean, but actually we also know that whenever we have to install rubber bearings, we also need to cover all the supporting points of the structure, so that maybe a hybrid system is needed. So we need both rubber bearings and flat sliders, and the flat sliders are represented by a purely frictional response. So that is, even though this is a very limited response, because we want the friction coefficient to be a very low number, because we don't want actually to obtain some mismatching between what we have guessed at the beginning for design and what we find at the end of all the computations for the nonlinear time history analysis. But nonetheless, we know that the frictional response is something very highly nonlinear, hysteretic. So for sure, for any standard code, I think worldwide, as soon as you have something highly nonlinear, you are not able to perform linear dynamic analysis. So just a response spectrum, I mean, but you have to go through nonlinear time history analysis. So by performing time histories. With the proper definition actually of the nonlinear behavior of some elements of the structure, for us will be surely the proper modeling aspects of the isolation devices. So there are a number of rules to actually ensuring the proper spectrum compatibility with respect to the target spectrum. The main result will be to consider seismic events, which are actually comparable with respect to the assumed response spectrum with respect to the acceleration values. And so what is generally done in both practice and research is represented by two strategies. And the first one is shown in this slide, in this figure. You can see that all the spectral coordinates for the selected events, okay, here there are 29, they are actually equal when we have a structural period equal to 1 second. That is a conditional compatibility, which means that we want all the spectra to have the same spectral coordinate in terms of acceleration, spectral acceleration at a given number of self period. And so whatever whatever values they assume in other ranges of period, we want to actually control the spectral coordinate given at a specific value of period, which means that we are pretty sure about the vibration period of the building rather than of the structural system. It can be actually computed with a certain amount of uncertainty, with a limited amount of uncertainty. And so we can just provide the spectrum compatibility by ensuring that the overall behavior of the response spectrum from the acceleration point of view is lumped at the same value for all the spectra for a given at that number of cell period. That is actually, as I told you, when we are pretty sure about the numerical value of the vibration period for our system. But generally, and I think that in most of cases, we are not pretty sure about that because there are a number of uncertainties about the modeling, about the distribution of masses, which are the stiffness of the elements, which are actually the main ingredients of model analysis, and so about the model shapes and specifically also the numerical values of vibration periods. So whenever we are not sure about the results of model analysis, we can perform the ordinary spectral compatibility, which I say ordinary because maybe what I've seen, this is the most common strategy for spectral compatibility of selection of events worldwide. So simply because it is quite hard to be pretty sure about model analysis results. And what is generally done in practice and what is generally ruled in standard codes for many countries is to provide the spectrum compatibility with respect to the target display, to the target spectrum in a period range of values. So in this particular figure, you will see that the bounds, the limits for this period range are bounded between 0.15, 0.15 seconds and 1.8. And there are also the spectral compatibility checks, which are done actually by considering the average spectrum among all the selected events as soon as we adopt a selection of at least 7 recordings. Okay, so this is a very important aspect. We can consider the average by considering also the response spectrum for all the events at the elastic one at 5% damping. This is important. This is also ruled in many codes. We have to check the spectrum compatibility with respect to the actually to the 5% damping ratio response spectrum. So this is important, and we check that the average spectrum within the period range is bounded between 90% and 130% of the target spectrum. So you see the dashed response spectra are actually the lower and the upper bound. And so this defines actually the limits for all the spectral coordinates of the average spectrum among the selected events. To be actually within, to fall within that range of plus 30% and minus 10% with respect to the target values. And this is actually what we are going to use both today for the selection, and then actually this selection will be applied tomorrow for the seismic assessment. And there are a number of issues for the selection. The selection can be done in two typologies of seismic events. The first one, which is the easiest one, there are a number of softwares which are able to provide artificial earthquakes. So this means that the software returns artificial signals which can be represented by the response spectrum, which is quite close, very close to the target one, which is actually an input for the software. And this is done directly according to special mathematical algorithms. And For sure, this is something unrealistic because actually it is something artificial and it is something which is synthesized by the software according to mathematical rules. But at least that will be, again, as well as in the natural events case, that will be exactly the case of a time series of a ground acceleration with the proper spectrum, response spectrum from the acceleration point of view. So that is a strategy. The other one, obviously, is to use the natural events, so recorded earthquakes within the history, so the earthquake catalog for a given country. And there are a number of databases worldwide where we can find actually and export some recordings for the most important events. And there are a lot of issues about that because actually recordings are related to real earthquakes. So they have actually that amount of amplitude for that duration, and they actually have a fixed response spectrum directly related to their characteristics. So whenever we have to match those events with respect to our target spectrum, we can have some difficulties in finding a selection of natural events, and that this is actually the main issue when we have to consider real earthquakes for nonlinear time history analysis. The difficulties in finding actually a useful selection for the input, for the definition of the seismic input. And generally, there is another issue for this because in order to match the proper response spectrum for the given event, we should apply some scaling factor to all the components. And so this means that we are actually modifying the realistic earthquake which has occurred in the past. This is a big issue because actually there is no limit, there's no limitation within the standard codes about the scaling factor for ground motions. And this is something strange, and for sure this is something that will change in the revisions of the main standard codes, because actually if we assume a given earthquake and then we multiply the ground motion time series by 10, what we obtain is rather than a realistic earthquake, because actually we have multiplied by 10 all the amplitudes of the acceleration values, but actually the frequency content of the signal is not comparable with respect to the amplitude which are obtained by scaling by 10. And so this is a big issue. So there are a number of limitations provided in research activities, and this is actually what we want to consider. But actually, these limitations, first of all, are not provided within codes, so with the standards, and actually they are neither provided by standards nor provided within softwares for selections. So we have to check it actually for whenever we get a selection, whatever is the software, we should check actually the amplitude of the scaling factor for all the events, not to be so too much high and not to be too much low. Also, the same reasoning can be applied if I scale by 10. I mean, if I divide by 10 all the amplitudes, also all the values of acceleration, this means that I get an earthquake which is not consistent with the frequency content of the original signal. If we just apply a scaling factor, we don't change at all the frequency content of a signal. So we are keeping fixed the frequency content of the signal by increasing or decreasing the amplitude, so the values. So this is the main issue, because if we scale, we are not changing any frequency content of the original signal. And maybe there are also some softwares which are actually influencing the frequency content. There are a number of them which use a wavelet the wavelength theory. I will show some of them at the end of this presentation. And they can be used, but actually they use wavelength theory for the definition of a matched, let's say a matched version of a natural earthquake, but at least at the end of the matching procedure, it is no longer a natural earthquake. That will be something artificial. So let's see some rules coming from standard codes. We will consider firstly the European one, the Eurocode 8, and then we will see what changes within the Italian building code, which is the most revised one, the most recent, which has been just revised in 2018. And for what generally happens, there are prescriptions for artificial accelerograms because they can be easily computed through softwares, and then there is some additional rules for natural seismic events. Also because of whatever is prescribed for artificial earthquakes is also prescribed for natural seismic events. So this is the paragraph of Eurocode 8 for artificial accelerograms, whenever we have to consider the seismic action as a time series of ground motion values in terms of ground acceleration. So we see that according to the artificial accelerograms, they have to be generated so as to match the elastic response spectra, given, okay, here in these paragraphs, all the spectra for horizontal and vertical directions are defined. And you see this is important for 5% viscous damping. This is a general rule. So this is important because we don't want to match actually our single event response with respect to the target one by considering an estimation of the viscous damping of the system, because actually if the overall system is nonlinear, that could be also not a single value, but that should be evaluated through iterative procedures. So according to the standards, this is not something that we have to guess at the beginning, but we have just to start with the 5% viscous damping. What we guess initially, for what we have guessed yesterday, is just something for pre-design the seismic isolation system, but actually that should not be applied. I mean, all the damping ratios for the technologies of the implemented devices shall not be guessed also for the selection of the seismic input. Otherwise, there should be a specific choice of the structural engineer also for the definition of the seismic input, and this can be also affected by some mistakes, and so standard codes do not want to have this eventual opportunity. So we just have to focus on 5% damping. Then the duration shall be consistent with the magnitude and other relevant features for also the value of the peak ground acceleration. But generally, we can say there is another prescriptions within the Italian building code that according to which we have to consider a minimum duration for artificial accelerograms of 25 seconds. And then when site-specific data are not available, the minimum duration of the stationary part of the accelerogram should be equal to 10 seconds. And this is because whenever we have to generate some artificial accelerograms, we have to consider what is known as actually the envelope function. So I mean, there are a number of softwares which can generate some artificial accelerograms, and we are expecting to find, let's call it X ground acceleration, so double derivative with respect to time. So we know that the accelerogram is something like this. It is actually a recording of acceleration values with respect to time, and then goes towards 0. So the input actually is for the software is the maximum the PGA of the related to the seismic hazard, and generally the response spectrum related to the seismic hazard. But there is another input which is very important, which is actually the envelope function. Which is actually a function which provides the let's say the boundaries for the whole the maximum, the minimum boundaries for the whole signal which is returned by the software. So that could be that function could have actually different definitions. One of the most common is something like this. There is a linear branch, and then a stationary branch, which is actually a constant amplitude branch for the envelope function, and that it could be again linear rather than exponential, and then also for the negative values. Okay, so this envelope function should have the stationary part at least of 10 seconds of duration. So the duration of the stationary part, which is this branch, according to Eurocode 8, should be higher than 10 seconds. Okay. Then generally we have linear and linear rather than curvilinear. There are also other in research which are highly nonlinear for the whole duration. And we consider generally a duration, total duration of 25 seconds minimum, so higher than 25 seconds. So generally, if we assume linear branches, we can also try to do this to consider 10 seconds for the stationary part, 5 seconds for the I mean the first ramp. So these can be 5 seconds, and then the final decreasing part of the signal can have an envelope function, a reducing function of 10 seconds again. Okay, so 10 seconds plus 10 seconds plus 5 seconds, we have 25. So this is a very general rule. There is an envelope function which is commonly adopted for non-structural elements, which is just a trapezoidal one with the initial ramp and the final ramp, decreasing ramp with 5 second duration, both of them. And then if we consider 25 seconds of total duration, obviously we have a 15 stationary part in the middle. That could be consistent with the prescription of Eurocode 8, and it is, as I mentioned, generally applied to non-structural elements. So these are the main characteristics for artificial accelegrams for Eurocode 8, but there are also other prescriptions in the next slide. And these are the suite of artificial accelegrams. I should observe also these rules. You see at a minimum of 3 accelegrams is used. But actually, if we check also the prescriptions of the Italian building code, whenever we use 3 accelegrams, we don't have to look at the average response parameter, but we have to look at the maximum value of among all the events, which are just 3. So this means that if we are looking at the displacement at the isolation system, we don't have to compute the average displacement among the, for instance, 7 accelegrams, but if we just apply 3, a selection of 3 seismic events, we have to consider the maximum one, which is actually a sort of way to overestimate the response, just because we are not considering a high number of situations and configurations of the seismic action. So what is generally assumed is to consider at least 7 accelerograms in order to consider the average response and not the maximum one, because actually what we are looking at is the nonlinear time history analysis response of our system, and we know that we will ensure for the spectrum compatibility of the selection, but for sure the single event can lead to a much higher response with respect to the target one. So if we adopt just 3 accelerograms and then we take the maximum, maybe the maximum is related to a much severe seismic event with respect to the target seismic action provided by the standards. So maybe we are overestimating the overall response rather than considering maybe a selection of 7. And so we don't have to compute the maximum, but the average. So the average will be for sure lower than the maximum among just 3 selections. Maybe it is highly probable, let's say. Then the mean of the 0 period spectral response is not smaller than actually the value at the 0 period for the target spectrum, which is generally assumed as AG times S, whereas is, as you know, the multiplication factor related to the soil conditions. And then you see within the range of periods between 20% of T1 and 200% of T1, where T1 is the fundamental period of the structure in the direction where the accelerogram will be applied. So T1 is actually the fundamental period, so related to the first mode of the structure. And these percentages rule directly the range of periods where we have to ensure the spectrum compatibility. And no value you see in point C of the mean 5% damping elastic spectrum, again, is highlighted the 5% damping from all the time histories. So the mean, again, is less than 90% of the corresponding value at 5% damping elastic response spectrum provided by the code. And so this means that the Eurocode 8 just provides a lower bound for spectrum compatibility. So for all the spectral coordinates at all period levels within the time, the period range, 0.2 T1 and twice T1. This is something that has been revised within the Italian building code in 2018. So there is no longer just a lower bound at 90% of the target spectrum, but there is also an upper bound. We will see it is exactly the one I've shown in the previous slides, which is actually 30% more than the target spectrum. So this means that the all the values should be bounded between 90% and 130% of the target spectrum for all the periods which fall within the period range. And I just want to highlight that, as you see in point B, there is the definition of period range, which is defined regardless the structure is seismically isolated or not, or in a fixed base configuration. This is also something different with respect to the Italian building code because there is the actual distinction between seismically isolated structures and ordinary structures. And we will see what I mean. The final prescriptions are related to recorded or simulated accelerograms. Okay, recorded are just real earthquakes which occurred in the past. Rather than simulated accelerograms. So that is actually related to earthquake geotechnical engineering. So if we are able actually to simulate the surface rupture which originates the earthquake itself, that should be done according to the proper softwares of modeling soils. And so on. So we will deal with the recorded signals, and you see that whatever is ruled for the accelerogram, the artificial accelerograms is also applied to recorded signals. And there are also some other issues related to the seismogenetic features, which originates the occurred earthquake should be consistent with respect to the construction site that we are considering. And there are also some other issues which are actually the ones that we have already discussed. So actually, this is what is ruled nowadays by Eurocode, which is actually under review. But these are the main innovative aspects which will be also implemented within the Eurocode. So these are in the Italian building code. So you see the mean spectrum among all the selected events shall be bounded between 90% and 130% of the target spectrum within the reference period range. So we have both the lower bound and the upper bound for all the spectral coordinates within the period range. And I just provide here the definition of the period range for the seismically isolated structural systems, which is bounded between 0.15 seconds and 1.2 times the isolation period assuming design. So this means that the lower bound is fixed, and instead of what is ruled in Eurocode 8, as you remind, the lower bound of the period range was 20% of the period of the fundamental period of the system. Here it is a fixed value, and then we have 20% more and an increasing of 20%, let's say, of the isolation period, instead of having twice the isolation, the fundamental period. Also because twice the isolation period would not be applied to the general, to the general response spectrum provided by codes, because generally we assume that the maximum period for response spectra are 4 seconds for ordinary applications. So if we generally consider values of isolation periods like the ones that we have considered yesterday for pre-design, we have assumed 3 seconds rather than 2.5. So generally we will get to twice 2.5, which is 5 seconds of isolation periods, and that would not be something realistic whenever we have to come up with some realistic device to be designed. So instead of the 1.2 T isolation, which leads to, if we even though we would assume 3 seconds for design, we will get 3.6, which is lower than 4, and that would be an ordinary application for the seismic action. And then these are additional recommendations. So for scaled natural events, this is what I meant before. As soon as natural events are just related to realistic earthquakes, they cannot be, they have fixed properties, let's say. So they have to be scaled in order to achieve the best spectrum compatibility with respect to the target spectrum. And in order to do this, we also have to ensure that we are applying scale factors which are meaningful. So they have to be bounded within certain ranges. And the main suggestions which are provided, and the main limits, which are limitations, which are provided within research activities, are 0.5 as a lower bound and 2 as an upper bound. Because we don't want to obtain unrealistic signals at the end, because whenever we scale a signal, we are not actually changing the frequency content, whereas we are changing the amplitude of the signal. So there is a mismatching between the two contents. And then even though you have seen that a minimum number of 3 accelerograms shall be adopted for nonlinear time history analysis, 7 ground motions shall be applied in order to consider the mean response among the selected events. Because if we consider the mean response, maybe we are able not to overestimate the overall response, and maybe we have not also to over design all the isolation devices and also the elements for the superstructure. So before seeing the softwares, I just want to ask if there is any questions about this. Okay, good.
Yes,
So,
I
yes,
have a question. I don't know if it's too early to ask, but I could see that the selection of ground motion will eventually depend on the period of the structure in order,
yes,
to select the matching range. But
yeah,
for our case, it's going to be the overall period of the equivalent system, right? Because we assume our system together, the isolation plus the building as a single degree of freedom. So
yeah,
that period would be the basis for our selection. Is it true?
yeah, exactly. So we generally assume the period that we considered yesterday in design, and that is what defines the upper bound of the period range. So this 1.2 time isolation, period isolation, sorry. And you see that for seismically isolated structures, we have approximately the whole spectrum for which has to be considered for spectrum compatibility, simply because okay, we are thinking we are already talking about model analysis, even though we apply something nonlinear, which is actually the isolation system, because okay, it is not linear, but we consider the equivalent period, something linear elastic, equivalent linear elastic behavior. And
Does
actually, yeah, this
does
is
the
the,
same? Yeah,
yes,
yeah.
yeah, just I just want to finish this reasoning because actually we have to consider the whole approximately the whole spectrum, because we have for sure the fundamental period, which is related to the isolated system, but we will surely have some higher modes which are directly related to the fixed base configuration. So this is the reason why we are considering approximately the whole period range for the target spectrum.
Yes, exactly. It covers a lot of period.
Yeah,
This rule exists only in the Italian building code, but does it exist in Eurocode 8
yeah,
or no?
exactly. Yeah, so you have seen that for Eurocode 8, you consider 20% of the design period of the fundamental period of the system. And so it is not a fixed value. So if we consider, for instance, 1.5 or two, no, let's consider 2 seconds. So the 20% is actually 1/5 of the period, and so you get actually 2/5, which is 0.4, which is much higher than 0.15 seconds. And
I would say the Italian code is a bit, let's say, more strict because think
yeah,
about the period that we considered yesterday. It was like 2.5. Let's say it's 2 seconds and you consider 20% of the 2 seconds, it's still 0.4 seconds, like
yeah,
approximately 2.5 times the 0.15 imposed by the Italian code.
yes,
So it looks
sure.
like that the Italian code asks you to consider a matching range that's too much bigger compared to probably not much bigger. On the low period side, it's way bigger than the Eurocode 8,
Yeah,
right?
sure. Also because the generally the higher modes, it is true that they are very important because they are related to the structural response of the building, generally the superstructure. But it is also true that they should be related to very low values of mesh ratios, of participating mesh ratios. So should not we should not find something very influencing the overall response for higher modes. But this is what I mentioned regarding the actual difficulties in finding the selections of events because of these very wide ranges of periods. So generally, okay, we have to ensure the spectrum compatibility with respect to the mean spectrum if we adopt actually more than 7, at least 7 earthquakes. But we have to ensure spectrum compatibility for the whole, approximately for the whole spectrum, which is not quite easy.
Yeah, I understand. Thank you.
Yeah, you're welcome. So if there is no other questions, I just want you to have a look at some tools for selections and for modifications or generation of seismic input signals for both natural and artificial ones. So the first one is this software, which is Rexel, and it has been developed within the Italian territory. This is by Iervolino et al. There is also a reference article which is published. I don't remember the journal, but whenever you open this software, there is a reminder that reminds you to consider also what in your works to cite also that that original research. So that will be every time you open the software, there will be a reminder that remind to cite actually this article. But this is very useful because it has a very large database of natural seismic events, and you see that we will see how to use it, and you can set the upper lower tolerance and actually which are 10% and 30% for what concerns the Italian building code. And then you have just to type the T1 or T2, which are the limitations for the period range. And then for the Italian territory, but you can do this also with the custom response spectrum. So you can load a custom response spectrum, and then you can directly consider the selection of among the databases which are implemented. And this is an example of the return results. You see there are, okay, these are just names for all the records which are related to occurred realistic earthquakes. You are also given to some Excel files which actually list all the events with all the characteristics and so on. So what generally happens within this software is that all the events are directly scaled in order to match let's say, in order to achieve the best spectrum compatibility. So I think that I think to remember that this software achieves the best solution for spectrum compatibility by minimizing the variance among all the possible selections, and so this is one of the reasons why this software may takes forever to run, actually to find a selection of events. So maybe we don't have the patience to attend and to wait for a very long time, so we have to stop the analysis and to try to do something else. But there are also other softwares which are actually softwares by the Seismosoft company, and there are these are two of them which I used in my applications. And the first is Seismomatch, which is actually the one I was mentioning before. So this software wants as input natural events, and according to the wavelet algorithm, which is actually proposed within the scientific literature, the software modifies the frequency content in order to better match the target spectrum. So actually what happens is that you start from a natural seismic event, and what you get at the end is actually something more artificial, let's say, but with the response spectrum which is approximately equal point by point to the target one. So you start from the natural one, but you get the result as an artificial one. So something very strange. I don't know if what you get at the end is something that you can call again natural events, because okay, it is highly modified through the wavelet algorithm, but at least you have started from a real earthquake, let's say. But then if you want something purely artificial, there is Seismoartif, as you may understand from the name of the software. It is capable of generating artificial signals within actually the period range and the upper lower bound of a given target spectrum. And this can be done according to different algorithms, which are described according to different envelope functions, as we discussed before. They are just artificial. So we are pretty sure that the response spectrum of the generated signal will be very close to the target one for all the values of periods within the period range that you define within the software. And so generally, okay, you are sure with the artificial signals that you are applying a consistent seismic action with respect to the target one. Yes, with respect to the target one provided by the code. But maybe, okay, you are considering for sure a selection of 7 events, but they are just 7 artificial events, so maybe they lead to very similar responses. Okay, so yeah, you will consider the average, and for sure you are expecting to find something, some final results which have very low coefficient of variations. I mean, with respect to the mean value, to the average value. So this is very fast because the generation can be done very easily by these softwares. So maybe you can adopt artificial earthquakes whenever you have you are in the design phase, so that you have to check, but you want to check not just with very handmade computations. Something that we did yesterday, but you want at least to do some nonlinear time history analysis. On Thursday, we will see some rules to carry out nonlinear time history analysis with a single degree of freedom oscillators with the proper nonlinear behavior for the isolation devices. And so this maybe can be done with artificial signals so that you can check if what you have designed is something which makes sense or not. But then I think that the most, suitable input signal can be referred as natural seismic events. Then you can match them with this software, but at the end you find something artificial for sure. Okay, I think we are done. I've just left some empty spaces here if we need to write something, and I think it will be the case at the end because we will try to check some results for the input signals. Okay, before starting looking at the softwares, here I've just reported Seismomatch and Seismoartif. I know that there is a new one, which is Seismoselect, which should be something similar to Rexel, so which is able to provide a selection of events according to some databases installed within the program. The only difference is that the database may be, I think, may not be available to users, but exception made for Excel software. As you have seen, I will show how to check all the actually all the events in both the response spectra and the signals points of view. So I just opened the software. So you see, okay, there is this black window, but at the end you will see this is defined. You see this is warning. If you want to use this software, please cite as and this is actually the okay, Bulletin of Earthquake Engineering. This is the journal. You can also directly download the paper or just press skip. You will have to press skip whenever you want to use this software. Okay, so this is the graphical interface, and you see that there is the graphics of MATLAB, because graphical user interface programs can be done within the MATLAB environment. And you can set in this region the target spectrum according to a number of, you see, Italian building code, Eurocode 8, the United States one, or rather than user-defined, where you can just upload a user-defined spectrum. So we can consider the Italian building code. We will set our longitude and latitude values for our construction site, and we will also have to consider the site class. We have set class C, topography category T1, 50 years, and functional type 2, which means that the reference life of the structural system is actually 50 years. So the coefficient which multiplies the nominal life is equal to 1. And the limit state for us is SLC, which means 5% of probability of exceedance within the reference life of the structure. And we are looking at the horizontal component. So the first step is just to press build code spectrum, and we want to do this, but we have just to check the longitude and latitude coordinates. For the proper definition. You see, if we press map, there is the Italian territory, and you have to check, okay, L'Aquila for sure is not here, but it is somewhere here, so that you can see if you are doing something right or not. Okay, so according to the Wikipedia, we have actually these coordinates. Okay, they have to be changed because actually we have a different coordinate. Okay, we have these the decimal coordinates. So we have here 13.391992, whereas here we have 42.354008. Okay, let's have a look at the map. Okay, this is something more related to L'Aquila site. Okay, so now everything here is right according to our response spectrum. Let's build the code. So you press here and we find these graphical result. I just want to check if this looks right. I just go back very briefly to the Express spreadsheet that we have built yesterday for pre-design. This was, you remember, the response spectrum. So we have the plateau defined according to 98% of G, and we start from 40% of G. And this looks like what happens here. Yeah, we start from actually 0.4 G, and we get close to 1 G. So in the plateau, so it looks actually the right one. Okay. So for the selection of the seismic events, we should check some other parameters. And the general rules refers to the disaggregation study for the selected construction site. So you see that according to this software, you can provide the disaggregation study according to 0 seconds value period value rather than 0.5, 1 second, 1.5 for the by considering the magnitude and the epicentral distance values. So this is the general rules that we generally consider. If you click on look at disaggregation, you have to wait a little bit, but then we will get the disaggregation study. I hope you all know what I mean. So there will be a graph. Okay, this is there is a warning. Disaggregation results refer to a specific study independent of the official Italian hazard data, but this is at least something very useful. And this is actually what I meant. This is the bar plot, the 3D bar plot, which provides the hazard contribution rate with respect to the definition of the seismic hazard of a given construction site with respect to the epicentral distance and the magnitude of the seismic event. This should be helpful for us to select all the events because we should provide some limitations for both the epicentral distance and the magnitude of the seismic events, where we have the highest contribution in the definition of the seismic hazard. Which means wherever we have the highest columns in these bar plots, we should consider the values for epicentral distance and magnitude. So I think that according to this drawing, we should consider epicentral distances lower than 20 kilometers. So we are considering all these brown columns. And then we can consider 5.3, let's say 5 as a lower bound for the magnitude. And then we can consider 7.5. So we can consider all of these. Because it is true that if you consider everything, you are also providing much more probability to get a selection, the proper selection of events. But it's also true that you are also enlarging the duration of run for this software. So it is better if you are able to limit some sort of parameters in terms of magnitude and epicentral distance. So once we have seen the hazard contribution through the disaggregation study, we can do the preliminary database check. Okay, based on you see, we can do a number of selections. So what we want to consider is just the magnitude and the epicentral distance. So we have said that we consider a minimum magnitude of 5 and the maximum of 7.5. And then we go from 0 kilometers to 20 kilometers. Okay. Then database, we have different databases and we can just start from the European Strong Motion database. And then site class. It is obvious that the best solution, the best choice would be to consider the same site class as the target spectrum. So we have set the site class C for our construction site. So we would consider just site C also for these records. Okay. Okay, we can start from this, but generally what happens is that we are not able to find a selection, so that we have to change. Okay, so whatever, any site class, but let's start from say as target spectrum because maybe there will be some results. So you click check database. Okay, and there are some records, so 30 events. And then you see there is the spectrum matching, so the lower tolerance, the upper tolerance, minus 10% and 30% for the upper bound. This is 0.15. It is the lower bound for the Italian building code. For T2, which is the upper bound for the period range. Okay, for our pre-design, we consider the 2.6 for rubber bearings and lead rubber bearings, but also for curved surface ladder. Okay, let's consider 2.6, and 2.6 times 1.2 is 3.12. Okay, let's say 3.2. This will be our upper bound. So we can plot spectral bounds. And this is, you see, we have bounds for the period range and also upper lower bound for the tolerances of the target spectrum. So here, analysis options. You see, we could also consider selection of unscaled records. That would be the best choice, simply because we don't have to look at the actual scaling factors for the selected events at the end, but we just consider realistic earthquakes as they have been recorded when they occurred, okay, with no scale factor. So let's try this. So we just uncheck this checkbox, And then you see I'm feeling lucky is a checkbox which says returns only the first combination found, which means that there is no optimization with respect to the variance of all the solutions found within the software. Okay, so let's just check. I'm feeling lucky, and if we are really lucky, we get a selection. Then we can set size individual record if you want just one, and then 7 records rather than 30 records. Okay, and then one component rather than 2 components. Let's consider at the beginning just one component. Let's check. You press, and then you see the software says that the time duration will be very long if anything looks working properly. You have just to stop it through the Windows Task Manager, and this looks like the case because generally solutions are found. I would not say immediately, but generally when you have to wait some time, this means that it is not actually working. Maybe because we are saying something very strict, because we have set same site class as target spectrum, then unscaled records, and then 7 records for the selection. So I think that this is quite hard to be provided. So I think that we can stop the analysis maybe, but let's trust on the software. But in the meantime, I just want you to see what I meant for the about the database of the software. You see, this is a folder where I copied these 2 folders where I have actually the all records which are listed within the software, and also within the 3 databases. So this is IT, stands for the Italian database, and then we have the IN, which is actually the European one, and then 00 stands for the other one, the Simbad database. So we have, and for all of them, you see that we have X component, Y component, and Z component. So it is very useful for us to have this selection of earthquakes, because then we can maybe set some script in MATLAB which allows us to select our events in a more controlled way, let's say. And the same also happens for the response spectra. You see, for all of them, we have already the spectra computed at 5% damping with X, Y, and Z component. So I just open MATLAB just to see, let you see what I mean. In the meantime, okay, it is still running. So here we have 25 of 80. Maybe we can also try to wait a little bit to see actually if it works. In the meantime, do you have any question? Okay, you see, it is terminated successfully in the sense that we successfully found 0 compatible sets. So I don't know how it can say successfully, but let's say it is at least terminated. So there is no compatible set found. So let's try to, okay, first of all, to wake the program, because I think that, okay, let's close MATLAB. And then, okay, let's try to change something. So let's remove the site class, same as target spectrum. Let's set any site class, check database. Okay, we have more than 100 records, very long time. The software itself says this, so we are actually done. Same matching tolerances. Okay, let's try again unscaled records. One component. it should be much faster. Okay, so you see, whenever we set any site class, that the probability is much higher. So you see, this is our selection, and the average spectrum is quite close to the target one, at least when we have the period ranges, which are the most important ones for us for the case study structures that we have designed yesterday, so 2.6. So the blue line is very close to the target one, which is the black continuous line. And then within the period range, the spectral coordinates for the average spectrum is very close, is within the upper and the lower bounds for the target spectrum. Okay, that could be our selection. We will try also to consider these also in the MATLAB environment, so that maybe these are unscaled. Okay, so let's check if we can just modify these just with a few scale factors in order to better achieve the spectrum compatibility. So I try to to export the selection. I think that we have to go here and then output the target results horizontal. Okay, I don't think this is okay. Displacement spectra info plot and get set. Okay, get set, that should be okay. So this is actually returned by the software. We have the information about all the events. You see, we have the waveform ID, which is actually the number of the file, the earthquake ID, station where it has been recorded, the earthquake name, the date of the events, the magnitude, the moment magnitude. Otherwise, after 7, it doesn't make any sense. Default mechanism, the central distance. You see that they are lower than 20 kilometers. And then PGA X, PGA Y, and then PGV, and so on. Site class, Eurocode site class, we have A, B, C, C, D. Okay, we have the whole alphabet, but unfortunately, this was the only assumption. The other strategy could be also to consider same site class as target spectrum, but by considering scaled events. But when you have to consider scaled events, actually you are in a certain way you are bounding not the single even scale factor but the average scale factor. So this means that you set 2 as the average scale factor, but maybe the single even scale factor could achieve also 5. So it is better if we can find a selection of unscaled events. Okay, so okay, I can close this. And then you see we have record and spectrum. Let's consider all of these, and we copy these also the target spectrum within our folder selection. Okay. Okay. So let's create a new script just to analyze the selection, and we want to consider a selection analysis B1. Okay. So how they are called? We want just to load the target spectrum horizontal. So we are able to, so they are actually text files. You see, okay, we start from the 18, and then okay, let's do like this. Let's erase the previous lines so that it's easier for us to load the files, and so also for the records. Okay. Okay, they are already with no. You can see my screen, right? Everything has stopped. Now should work again. Okay. Okay. Yeah, we are given already to just acceleration and time values. So we have two columns. So let's consider the list of of records. So this means that we want to consider whatever name times txt, but we want to at least records. Okay, record. Okay, so okay. If I press F5, we find 7 records. Okay, this is true. So let's consider all of them for I E. So the ith event equal from 1 to 7. Okay, generally the size of list in terms of number of columns. So in terms of loading the signals, we can use since they are just text files. We can use import data as expression. So let's call it x ground. Double P stands for second derivative, point, second derivative with respect to time, equal to import data of list event point name. Okay, and then we call the first column as the t vector. So we have xg point first column, and then we have this second column. Okay, and then we can plot our events. Okay, so these are our events. So we have some events. The last events which goes up to at least 1 G, 80% of G, 0.8 G. Okay, this is very strong earthquake. And I just remind that the PGA, the peak ground acceleration for our response spectrum, the target one was 40% of G. So you see, for the last events, we have 80%, but here we have 30%. Then, okay, approximately 50%. Then again, 38, 30, 35, 50%. Okay, again 50%, and so on. So we will consider the response spectrum for all of them. Let's check these. So I just want you to have some very fast solution to compute the response spectrum. There are softwares which can do that, but the easiest way is actually to do this by hand, by just a very fast script. So what I want to use is the following procedure, and we will use it also on Thursday with the the nonlinear integration of a single degree of freedom oscillators. So the time integration for a response spectrum we will refer to a number of period values, the ith value, okay? So given the ith value of period that we want to consider, we compute the angular frequency, the ith one, as 2 pi over the ith value of period, and then we consider the differential equation of motion for the single degree of freedom oscillator, relative acceleration plus 2c omega I relative velocity plus omega I squared relative displacement equal to minus xg second derivative. Okay, so this means that we will have an explicit time integration method which allows us to consider the overall response as the following, which means so the velocity at the time I plus 1 is equal to the velocity at the time I plus 1 over the t dt, the variation of time times minus xg acceleration at the height minus 2c omega and velocity at the height time instant minus omega squared at times displacement at the height time instant. Okay, and then we just compute the displacement at the height plus 1 equal to the previous displacement plus dt times the velocity that we have just computed. So this is a very fast algorithm to time integrate the overall response for a given single degree of freedom oscillator. So we will try to implement this to compute the response spectrum. Okay, so let's consider a different period vector, which goes from let's say for period values within our range of periods. Okay, every 1 over 100 seconds and up to 3.2. Okay, so we have for actually for IT, which goes from 1 to length of t. Okay. Okay, the time vector as already defined is already defined. Also the ground motion, and then we have just to predefine the displacement. The displacement vector, which is a row vector, and then also the velocity. Then we start from 2 to length of t. And then we see, okay, the velocity at the height equal to the velocity at the I minus 1 plus t I minus t I minus 1, which is dt, times minus 6g ground motion at the height, which is known, minus 2 times c, and we have to set it here 0.05 because we want to consider 5% damping. Let's consider here omega, which is 2 times pi divided by t. Okay, times omega at the height period, and times the velocity at the previous time step, and then plus omega it squared times the displacement at the previous time step. Okay, and then we have displacements like this. Once we have this, we can collect the maximum, actually the maximum acceleration. So the SA over IT is equal to the maximum of absolute value of, let's call it SD. So the displacement, so we have just to store the maximum value of the absolute, the maximum of the absolute value of displacements. And then we have the pseudo acceleration, which is actually the spectral displacement times omega squared. And that's it. Okay, we don't want to look at the ground motion time series, but we want to consider actually all the response spectra. So we have a figure 1, all, and when we want to plot the period and the pseudo acceleration. Okay, we have these, but because maybe we have something which does not work properly in the in some events. Let's check. Yeah, you see that something is not working properly. So there is something here which does not work. Let's check. So this is omega, and omega has proper numbers. Yes. Okay. So velocity, this is actually the time. Okay. Okay. Okay, let's check as usual, just one value of period. Let's consider just 1 second of period. Okay, we get just wrong values, but what I want to see is the displacement solution, which has actually these yeah, you see it is something very high, so we take forever to do this. So the main reason about this behavior is maybe because we are storing something wrong. So the damping is the same, yes, and it is right. Yes, dt times, okay, because we get actually the proper, yes, yes. And then the displacement. So it looks right as usual. What happens is that it looks right, but something is wrong. So maybe I don't think this is the, yeah. So in the meantime, I check these. We can directly also consider the spectrum here, but the easiest, you see, the target spectrum is sampled every at given numbers of periods. So let's check if they are sampled with the same vector. Yes, it looks like. So it is even better because if we use directly these, it is even better because they are sampled with the same vector. So we can also consider some correlation. So I will check this solution why it is actually wrong, but I don't know why, because everything looks like working properly. Because with respect to this, yes, yeah, that should work, but I don't know why it doesn't work. But I will check. So let's try to consider also the list of spectra. Okay, and then we will also consider this. So let's forget for a while about this, and then let's import the spectrum. Okay, so this is SA, and the period is SA first column, and then the SA is again SA but second column. Okay, and then figure 1, we hold all the spectra, and then that's it. Okay, this is the selection provided, and then we have also to upload the target one, the target SA equal to import data. This is the file name. Double T stands for target period vector equal to TSA first column. And then second column, figure 1, all, plot. And then let's bold the line. Okay, maybe this is given in G, so we have to multiply times G. Okay, so this is actually what we found for the okay, so there should be the problem. Let's check. Oh yeah, maybe I found the mistake. Yes. So it was just a symbol, which is here. There should be minus. Okay, because minus and minus. Okay. This is just the last try I want to consider. And okay, let's erase this. Okay. I don't know if okay, there isn't the figure. Okay, this is the figure. Let's check if it works before. Oh. No. Oh yeah, because this is just a period value. Okay, 0.015 and 3.2. Okay, so you see, this is actually there was a plus instead of a minus. So this is actually the same results that which are provided by the Spectra, just within our period range. So there is a huge variation for them. And I just wanted to you to see the time integration procedure, which now is right. There will be, you see here, there was a plus, but we have to subtract all these contributions. We will see these in detail on Thursday, when we will consider also the numerical hysteretic rules for all the devices. But maybe it is better for us now to consider the imported spectra, just because they are sampled within the same period vectors. So let's consider again the second version of the script. So this one. So let's erase his, and then here. Okay. So if you press F5, okay, we get exactly the same. So the only difference is that you see that they are sampled with the less points with respect to the others that we have computed manually. Okay, so that is the only difference. So there is a higher resolution for what we compute directly with this time integration procedure, because we have set this period with this period vector. So what I wanted you to consider is again the method that we considered in the numerical laboratory last week, which was the normal equations method for the least square procedure. Okay, but we will apply this to the spectrum compatibility. This is just a check if we are given to unscaled selection, like in this case, if we are able to actually scale all the events by scale factor, which are bounded between 0.5 and 2. And by computing the actual scale factor, considering a least square procedure, maybe we don't get something useful, but at least we try. So what I mean is the following. Okay. So according to the normal equations, we can consider that the the target spectrum is equal to alpha times the spectrum for the single event. and this is the single event spectrum. Okay, and this is the scale factor. Okay, and this works for this relation should work for the for all the points within our period range. Okay, so this and the most important thing is that we should sample both the target and the single event spectra according to the same period vector. This is the reason why we are using the already provided spectra. And we are also considering that the spectra are related to linear elastic systems, so that if the spectrum of alpha times the ground motion is actually equal to alpha times the response spectrum related to the ground motion. Okay. So let's say SA of alpha times XGW. Sorry, double point, so double derivative is equal to alpha times the response spectrum of the unscaled event. So a sort of linear proportionality of the input with respect to response spectrum. And this can be done since everything is linear elastic and the damping ratio is very low, so 5%. So what we can get is for each within our period range, we can get alpha, which is returned by normal equations method. And alpha, if we consider these as a vector, and they should be column vectors, both of them, we compute the inverse of SA, so the spectral acceleration of the single event transpose times SA single event to the -1 times spectral acceleration single event transpose times spectral acceleration target spectrum. Okay, let's try to see what numbers we get. Okay, so we want to consider these for the period ranges that are associated to our design application. Okay, so we have let's consider the indexes for the period bounded between 0.15 and t less than or equal to 3.2. Okay. Then we have S a single event is equal to SA in the. Okay. Okay, let's move this definition of the target spectrum upward because we need it at the beginning. And then as a target is equal to target SA at the indexes, same indexes, and then alpha at the ith event is equal to the inverse of SA single event transpose times SA single event times SA single event transpose times SA target. Okay, so let's check. Okay, the figure is always the same because we have not considered anything different. Okay, yeah, values are very low, but just because we have to multiply the target spectrum times 9.81. Okay, so we have just to remove this here. Okay, so here we have the same figure, and so we see, yeah, okay, we have to change a little bit because this means that the selection is already yeah, well done. But you see, according to these scaling factor, they are actually bounded between 0.5 and 2, because the minimum value, I think this is this one, which is 70%. So it is higher than 0.5, and the highest is 1.2. And these are returned by normal equations, and this means that we have found, according to the unscaled events, we have found the multiplication factor, the scaling factor for the single event, which provides the best fit, the best fit solution for the scaling procedure with respect to the target spectrum. Let's check if this is true. But in order to check it, we should be able to recompute actually the response spectra, because okay, it is true that we can consider the spectrum for alpha times the ground motion equal to alpha times the response spectrum of the unscaled event, but it is better for us to directly compute the response spectrum. This is the reason why I wanted you to see the time integration method. So once we have this vector, we store it with at the beginning. Okay. Alpha. Okay, and then we just comment this, and we just uncomment this. Okay, so our ground motion will be multiplied times alpha event, I event, and then we have to uncomment this and to say is pseudo. Okay, I think that this is done. Okay, so it is a little bit different than before, but you see, this is actually the best solution for the nonlinear best fit procedure. But we still have to check that even though we have computed this, yeah, it should be like that. But we have to ensure that with these, I mean. With these new scaling factors, instead of having the unscaled events, the spectrum compatibility is ensured. So we have to compute the average spectrum among the events and to check if it is bounded between 90% and 130%. So let's check it. So in order to do this, we have just to plot also bounds. So we have to plot 0.9 times and 1.3 times of the target spectrum. And then we have to plot the average one, which is T. And okay, to carry out the average, we should also store all the all the pseudo acceleration response spectra. So let's consider this. Okay, and then mean pseudo acceleration among the columns, I think. And we will color it like a continuous and red. Let's check if it works. Okay, so maybe we have to check some locations. Yeah, you see, there are some of the locations here which are not actually good, because okay, maybe here, yes. Okay, yeah, it goes beyond the 90%, but here there is a huge variation. Okay, and then also here. Okay, so it doesn't work with this, but we can just increase a little bit the target. So let's check if finally, if we assume just alpha as a unitary values. Otherwise, this is just a try, but yeah, otherwise we can just use the unscaled events, and that's it. 1/7. So if we use just unit values, okay, this is the final result that we got before. Okay, yes, this was the result of the program. Let's try to consider something different. So this means the normal equations for the actually not with respect to the target, but with respect to 1.1 target. Okay, so maybe we will get something different, and then if it doesn't work, we will just use the unscaled ones. So this is a method that I generally apply to see if I can just modify some actually some scaling factor in order to get closer single even results to the target spectrum. So let's try to do to comment this again, and then to uncomment this, and then here to do this. Okay. Okay, and this is okay. This is not obviously something. Okay. No, this is not okay. Let's consider times 1.1. Okay. So we get these results, which are actually directly 1.1 times the before. Okay, so let's go back. If we consider 1.1 times the older scale factors, no. And 1.2, but we are getting closer to the previous. Okay, maybe 1.15. Yeah, but this is approximately okay. Maybe here we are overcoming. Okay, I think that we can directly use the unscaled one. So because this is we were actually lucky because this is a good selection actually. You see that we don't have any a very significant variation. Everything is bounded, and at least here we have approximately the same values for between the target and the average. So I think this is fairly good. So we will use tomorrow the unscaled events. So the first results that we got through the software, and that's it. So do you have any questions about what we have? Okay. No problem for the time integration. We will see it again on Thursday, and this is just the easiest case for the linear system. We will use it also with the non-linear applications. So for all the typologies of our devices that we have considered. So any questions? Okay, if there is no questions. Thank you, and let's see you tomorrow for the numerical laboratory. I just remind you that tomorrow we will use SUP 2000, so we will have to apply this selection to and to the case study structure. First of all, we will have to build the finite element model of the structure, and then we will have to apply seismic events together with the nonlinear hysteretic behavior of devices. So if you need, some of you have already asked me the access to the computer in my faculty for the access to the software. So if you need, please email me within today to ask for the remote desktop link. Okay, see you tomorrow. Have a nice day.
See you tomorrow, Professor.
See you. Thank you.
Bye.
Thank you.